Okay. We have any chalk? Let's just make sure we have lots of chalk, shall we? Okay. All right. So last time I finished by talking about the basics in quantum Hall effects. And about the last thing I mentioned was that the basis functions for or a set of basis functions in a particular gauge for the lowest Landau level in the plane are basically proportional to power of z times this Gaussian, and m is again a non-negative integer. So these are like, in a sense, like simple harmonic oscillator states. So now I'm going to talk about some trial wave functions in the fractional quantum Hall effect, beginning from Laughlin. So a general wave function in the lowest Landau level for many particles now will have to be a combination of these basis functions. So it has to be some function of the n coordinates, and then we have this Gaussian which just hangs around, never changes. And f is a holomorphic function in each variable zi. And I'm going to refer to the particles with these, which have these coordinates, as particles. Chetan was using the term particle for quasi-particles. I'm going to consistently refer to my underlying particles, which may be electrons, as particles. I'll just say particles, and quasi-particles will mean quasi-particles, as I've discussed before. Yeah. M is a non-negative integer. Parameterizes different states. It's actually related to angular momentum. Does it really matter? What? These are functions in the lowest Landau level. So these many particle functions are lowest Landau level functions. F is a holomorphic function, and f will have to be a symmetric function for bosons and an anti-symmetric function for fermions. Okay, so these underlying particles are just ordinary particles, either fermions or bosons. All right, and so physically speaking, it will make sense to use these wave functions, states, with all the particles in the lowest Landau level. This will make sense if the interactions are weak compared with the energy for exciting a particle to the next Landau level, which is h bar omega c. So if the interaction potential is the typical interaction potential values, say at the particle splitting, are much less than this energy, then this is the kind of regime in which we can realistically use these functions. In any case, we'll just use these as functions and hopefully capture the physics of the quantum Hall effect. All right, so now I'll just write down this function proposed by Laughlin. And I have to keep writing this Gaussian. Okay, so we've made a particular choice for the function f. And again, q is an integer, positive, non-negative. Well, it better be a positive integer, really. Otherwise, I don't think I want to use this. And so to make the function here symmetric, then we need Q even for bosons and odd for fermions. For example, for electrons, then Q would have to be odd, so Q could be 1 or 3 or 5. And originally, Laughlin was trying to explain the 1/3 state, so this seems to fit quite nicely. Okay, so now we'll analyze this function. So the highest power of any single coordinate, zi, let's say, doesn't really matter which one, but if I expand out the wave function, the power in zi, the highest power of zi I can find, you can see is going to be when it's, if I select zi in every factor that it's, in which it appears, then there are n-1, because there are n-1 other particles, and that's raised to the power q, so I get q times n-1. And following what I already said yesterday, so we know that the functions are concentrated basically on radius square root of 2m on a circle, and so the largest radius for this circle is square root of this number, and we can identify that, we can think of that as enclosing a certain number of flux, which will identify as the number, so we'll call that the number of flux n phi. So I'll define this n phi to be the largest power that appears in the function. So this will be a good definition, at least for these sort of ground state functions. We'd have to reconsider this if we're looking at edge states, but that's not a story that I'm going to get into. Okay. All right, so now we can take this n phi and we can analyze the density. So we know the particles are all spread over these orbitals. M is the m's, the individual m's like this, for the particles are spread over these functions up to m max. And so if the density is uniform, this is the number of states. We have n phi plus 1 states. And so if we take the number of particles and divide by the number of states, n phi or n phi plus 1, it won't matter much because I'm going to take a limit, then I can define this to be the filling factor. And if we assume that the particles are spread uniformly, so the density is uniform out to this radius, if you like, r is square root of 2n phi. If you imagine they're uniform out to this radius, then this is basically the density of particles. This is the dimensionless density of particles. So the actual density would be nu over 2 pi. Well, in any case, you could say this is the average density. All right, so far we haven't done very much, but now we would like to continue and actually see if the density is uniform, among other things. So at least the first thing to do is just to try to study the density of particles in this state. So to study the density, what we'll do is we'll first take the mod square of the wave function and we'll write it in this form. So we can write it more easily by writing it as the exponential of the log, and I can take out a factor of q, and then I have sum on I less than j log zi minus zj absolute value squared minus 1 over 2q sum on j mod zj squared, all in the exponential. And then following Laughlin, we can identify this as the Boltzmann weight of a certain two-dimensional plasma. So Coulomb charges in 2 dimensions interact with a logarithmic potential, which is what we have here for each distinct pair ij. So we can describe it by saying that we think of particles of charge 1 formally, because the coefficient here is 1. And the mod zj squared for each particle is a background potential. So if you have a uniform charge density, it produces an electric field following Newton, really, or Gauss, which is linear in distance, so the potential is quadratic in the distance from the origin. So this quadratic potential corresponds to a uniform charge density. Or if you like, just take del squared of this and you'll see that it's constant. And so we have a uniform background, which is a neutralizing background with the opposite charge density. So the charge density in the background is minus 1 over 2 pi q if I use the same units. Okay, so the particles have positive charge and some density, which we'll figure out, and the background has negative charge density, which is uniform. And in addition, we have a temperature, and I'll say that this Q is inverse temperature, so the temperature is 1 over Q. So this kind of plasma was even studied before. It's a classical stat-mech problem. And in fact, the physics of this is really controlled by a single parameter. Although I've talked about it as charge 1 particles with some temperature, only the product of charge squared over temperature actually comes in to determine the physics. And that's basically just Q. So there's only really one parameter, which is Q. So the parameter is Q. So then what happens is that if the temperature is sufficiently high, the plasma should be in a screening phase. So it screens externally imposed potentials. And that means if Q is small enough. And so supposedly it's in a screening phase when Q is less than about 70. Although there may be better estimates of the number now. This is rather an old estimate. No, it's a classical stat-mech problem. If you want to do the classical stat-mech, you can integrate out the momentum in the usual way. You get a prefactor. Then you're just left with the interactions between particles.
What happens at lower temperatures?
At lower temperatures, this will form a crystal. This is not particularly relevant physically to our problem. Okay. And in practice, we'll be interested in moderate values of Q, not large values. Okay, so what does it mean to be in the screening phase? It means that the particles want to locally cancel the background negative charge density. So in any region, I want to have a number of particles that just cancels this. So the particles are spread rather uniformly. And because of this screening effect, it also means that the density correlations, it's not a crystal, it's a fluid, and the density correlations decay exponentially with distance. Or maybe even faster. Okay. And so this is the dominant property of a plasma in a screening phase, is that if I put in some additional charge, for example, like an impurity, the particles have to readjust. But what they do is they produce a local screening charge within a screening length, which cancels out that additional charge, so that if I just look at the total charge in a larger circle disk, then I still see zero net charge, including the particles, the background, and the impurity. And that's good with exponentially small corrections. So that's what screening means. Okay, so what happens here, we have to be a little careful because we have a finite number of particles, and I've got an infinite neutralizing background. That's a little bit flaky, but it's not going to affect anything at the moment. So what happens here, the way this is set up, is the particles will form a droplet. We know that there are basically none of them outside this radius. So we know that they're inside this radius R, which I already described. And because of screening, therefore, we get basically uniform density inside this disk, or droplet. Okay. If this R is large, if n is large, this is large, We get a uniform density in here, except maybe for at the edge we have some edge effects where the density is trying to drop to 0 and maybe some oscillations and things. And that's over some length scale which is of order 1. Basically well away from the edge, more than 1 unit of length, magnetic length from the edge, the density just becomes the uniform density. And this density has to cancel the background density, and so the density has to be 1 over 2 pi q, which again is nu over 2 pi. So indeed, the density actually is uniform inside this region. Yeah. Well, it's not going to be, yeah. I mean, yeah. First of all, the fact that it crystallizes for Q bigger than 70 does not mean that it describes the Wigner crystal in a real system. It's a trial wave function, and it's not going to be particularly useful in that region. So we're not really going to talk about Q bigger than 70. Okay. Okay. Now, incidentally, if Q is 1, in the special case Q is 1, then in fact there's the Vandermonde determinant identity which says that this product is actually equal to a determinant, and we simply get we can think of that as a Slater determinant where we fill all the orbitals from 0 up to n minus 1. So we just fill all the lowest orbitals. So if you imagine making that Slater determinant to fill the lowest lambda level, which I already referred to actually yesterday, then that wave function, that also has uniform density out to the edge, and because of this identity, it's actually the same as the Laughlin wave function for Q is 1. So it's a special case. And another comment, it's really a comment, and a second comment is that there's what I call a special Hamiltonian, or parent Hamiltonian, which is a Hamiltonian, really it's constructed in the lowest lambda level, and it's a Hamiltonian for which the Laughlin wave function is an exact zero energy eigenstate. It's a positive semi-definite Hamiltonian, and the Laughlin wave function is in fact the unique function of minimum angular momentum. This angular momentum is the only function with zero energy. And the reason you can construct this is because the wave function is going as zi minus zj to the q as zi tends to zj, and actually this is for Q bigger than 1. For Q is 1, it's just vacuous. There's nothing to say about it. And this power Q, whether I'm doing fermions or bosons, this is not the lowest power that's allowed by the particle statistics, which would be 0 for bosons, for example. It's some higher power, maybe 2 or 4. And that means that there are some terms not appearing in the state. And that means if I hit the state with some projection operator, some appropriate two-particle projection operator, that annihilates the state. Namely, if it's a projection onto having two bosons at the same point, it will annihilate the Laughlin wave function. So that's basically the origin of this special Hamiltonian, which I'm not going to go into more, really. Okay. What? Have what degeneracy? Correct. I don't know what's correct. If we're Laughlin, we don't know anything about that. We've just written this down for the first time. What's the degeneracy of this Hamiltonian? Well, this droplet is centered at the origin. So there is a degeneracy, which is I could translate it in the plane, so it's centered at a different point. That's the degeneracy. There's a center of mass degeneracy. All right, bear with me for a few more minutes, would you? I'm going to give the whole lecture. I'm not going to do it just in answer to your questions. I'm going to actually give the lecture. Okay. Well, on the subject of the special Hamiltonian, since I won't come back to it, we don't know how to prove that it has a gap in the bulk. Okay. So now let's go on to fractionally charged quasi-particles. Okay, so Laughlin also wrote down a function for what he calls a quasi-hole. So this is a kind of quasi-particle. So this is, I'll call this psi Laughlin plus W. And so we'll write an extra factor in the wave function, product of Zj minus W times the Laughlin function. So now in this function, you see that it vanishes when any particle coordinate is equal to W. So there can't be any density of particles at W. The density of particles now must vanish at W as an operator statement or as an expectation value, if you like. So we have some kind of hole in the density. And now if we apply the plasma mapping, we can take the log of this thing. Maybe I won't write the whole thing on the board again, but I'm basically taking the log of the mod square again, and then what I get here is I get an extra term, which is plus log sum on j, log mod Cj minus W squared, but I have a factor of q there, so I have 1 over q. So that's inside the square bracket. So this is acting like an impurity charge of magnitude plus 1 over q in the same units. Okay, so this is W is not a dynamical variable, it's just sitting there. If I want to calculate averages, I have to integrate over the zi's, but W is fixed. So W is just like this impurity that I mentioned before. It's just an impurity, and so therefore there's a net deficiency, there's a screening charge around this in the plasma. There's a deficiency of charge in the vicinity of W, and that deficiency of charge is exactly minus 1 over q because of screening. Can't take any other value. So that's the charge due to the particles. The net number of particles is, there's a hole in it. So if you like, you could imagine a plot of particle density versus position, and there's a hole at W. And there's a well-defined expectation, integral of expectation of charge relative to the uniform background missing from this region. And because of screening, this is exact. Okay. Now, of course, charges don't just disappear. So what happened to this? Well, of course, what's happened is that this factor has pushed particles away from W. The total number of particles is still n, so there must be some additional charge at the edge, if you like. So the droplet is now a little bit larger, such that the total number of particles is still n. So there's a little, if you like, compared with the original droplet, there's some charge sitting on the edge. Okay, so we can also construct, following Laughlin, a so-called quasi-electron state. And what Laughlin did was he replaced the z here by dz, acting on the factors other than the Gaussian, because that's the adjoint operator. But this is much harder to calculate with. it should have the basically opposite property. It should have the effect of having, it should have a charge of, so we now get an excess charge of 1 over q instead of a deficiency. But it's much harder to calculate with that. We can't use the plasma mapping in the same simple way. And furthermore, the quasi-electron function is, whereas the quasi-hole is very natural and anyone will want to use this function because it's so simple and nice. The quasi-electron function, well, different people have different ideas how to write some trial function down, and none of them is particularly nice to work with. So we tend to focus more on the quasi-holes than on the quasi-electrons. Okay. Well, we can, as I said, we can write something with d by dzj minus w bar on the Laughlin function. But, I mean, it's not going to tell you much. Yes, actually it does, because, as I said, I want to assume that the d by dz does not act on the Gaussian factor. Otherwise, I can adjust for that, and I can still do it in the lowest lambda level. Yeah.
What's wrong with just taking the reciprocal?
Well, that would not be in the lowest lambda level, would it? Because it has a pole.
But maybe if you figure
Well, only if, no, w is not a particle coordinate, so it has a pole at w. I mean, we would love to use that because it's a simple form and one can do the plasma mapping in the same way, but unfortunately it's not a lowest lambda level function. So there's pros and cons. You could try to argue, well, this is a great idea and we can use this conceptually to understand things, and I might be happy to do that. But if I follow Laughlin's, kind of game, then I want to stay in the lowest lambda level, just to do the physics. Okay. All right. So these are quasi-particles. These are trial wave functions for quasi-particles. Away from the position of the quasi-particle, the function just returns to being just the ground state. So locally, it looks like the original ground state. So it's a quasi-particle. And now let me also point out that if for one thing, I can make multiple quasi-holes. I can generalize this, and I can have several coordinates wk, let's say, and have a quasi-hole factor for each of those. So now I've got several quasi-holes dotted around in the sample. Now, in particular, I could take q quasi-holes and put them at the same place. In that case, you see, then I have the exponent q like I had in the original Laughlin wave function. And in fact, that function, if I don't have any other quasi-holes, let's say, if I just have q quasi-holes at one place, that function is exactly what I get if I take the Laughlin ground state with n plus 1 particles, and I apply a destruction operator, a field operator at w, to destroy one particle. So then I have n particles, and what happens is the location of the destruction operator replaces the extra coordinate, and let's say that the coordinate of the destruction operator is w. The function I get is exactly this function with exponent q here. So q quasi-holes are exactly equivalent to one, if you like, real hole, destroying a particle in the original Laughlin wave function with, of course, the appropriate particle number. Okay, so q quasi-holes is equivalent to a real hole. And you remember I said, and now let me imagine for a moment that particles are bosons. So the boson field operator fits my definition of a local operator from a couple of lectures ago, and they commute at different places. I'll view it as a local operator. So q quasi-holes, actually at the same place, are equivalent to a local operator. And so therefore, that's basically, apart from keeping track of the total particle number, it's the same as doing nothing, or the trivial quasi-particle. up to local operators. Okay. So that means that there are just Q types of quasi-particle in this system. Well, maybe I should convince you that there aren't any other kinds of quasi-particles apart from these Laughlin types that I've talked about here, but that's the case. So there are just Q types. So they can be labeled by charge. They have charge, let's say, little q over big Q, so that my little q is an integer. So they have charge, little q over big Q, but actually, if you like, I can take this to be z mod q, because if I change little q by big Q, then I come back to the same quasi-particle type up to a local operator. Is that clear? Okay, so I said that that's the case for if the particles are bosons, that's when Q is even. However, most of the logic goes through in exactly the same way if Q is odd and the particles are fermions. And now I want to say that Q quasi-holes are equivalent to applying the fermion destruction operator to make a real hole. And I would like to say exactly the same things there. The only fly in the ointment is that I said that fermion operators don't count as local. Well, I'm prepared to extend my definition a bit, and people sometimes go back and forth on the question whether a fermion operator should be viewed as something local or not. In quantum field theory, you would probably regard this as your local field operator. So we can change our point of view a bit and say, okay, in the case of Q odd and fermionic operators, then the fermion field operator, the particle field operator, counts as a local operator. Then we again have Q types of quasi-particle. Most things go through, but in fact, you don't get this for free. And when you get into the deeper structures of this modular tensor category, in which some of the ones I haven't talked about, I don't think Chetan's talked about them yet either, in particular the modular properties, they don't completely hold if you want to do this fermionic version. So the full modular properties hold when your underlying particles are bosons, and then you can just say you can happily say that a boson field operator is a local operator. And if you want to view fermions as local operators and do this type of thing in the arguments, well, there's a price for that, and you don't get full modular properties. I wouldn't put it that way. I would say that what happens is that you have to think of the system, well, it has to do with boundary conditions and things. You have to imagine some additional structure, so-called spin structure. You get invariance under a subgroup of the modular group, and some fairly unpleasant, more complicated things. It's much more convenient if everything was a boson. Okay. Of course, we would really like to talk about the fermionic case, because after all, it happens that we have fermions in the real world, and we'd like to view them as basic particles, and we can almost do so, or we can almost view them as local, but there's a price for that. And of course, when it comes to the Hamiltonian, with my original definition of local operator, I'm allowed to add those to the Hamiltonian. When it becomes fermionic, I still can't add it to the Hamiltonian. I have to add only bosonic local operators in the Hamiltonian, and therefore things that preserve fermion parity, the parity of the number of fermions. Okay. Nonetheless, many things work out the same, and it looks nice, even in the case when Q is odd and we have fermions. Okay. All right, so now, still following Laughlin, rather than some special Hamiltonian, I'm going to think in terms of a more generic Hamiltonian, which is a potential interaction, maybe a real Coulomb interaction between particles. And we can think of these functions as trial wave functions or variational wave functions. You could say variational, but there doesn't seem to be much you can vary. So it's called a trial wave function, meaning you just try it. Okay. So if we have a repulsive interaction, then we can take the expectation value of the interaction energy. So we can try to calculate the ground state energy. That's fine, but not very useful. What we really want to do is we want to calculate the change in the expectation value of a potential interaction when, to keep the particle number the same, let's say we had a quasi-electron and a quasi-hole. So we pop out a quasi-hole and quasi-electron from the ground state, from the vacuum, which means we don't have to change anything at infinity. We pop these out, move them apart, and then we can take the expectation value of some Coulomb potential, for example, a real Coulomb interaction, and the energetics of the state changes because we've done some things with the density. So we know things about the density in the state, so we can use that to try to estimate the Coulomb interaction. And because there's this local deficiency of charge in the core, then we get some change in the Coulomb interaction energy. So this is going to end up being non-zero because it's basically coming from the short-range behavior that we've changed. We've got a dip in the density somewhere, and we've got a maximum somewhere else. So we're going to have some Coulomb energy. We're also going to get a net interaction between these that falls off as distance. That's a separate thing. But asymptotically, when they're far apart, that drops out, and we just get an excitation energy for creating these two objects. And this will be non-zero, and this implies that there's an energy gap for creating these objects. Okay. So this is why then it was argued by Laughlin that this is a trial wave function for a many-particle correlated state which has an energy gap for these charged excitations and therefore behaves rather like the integer quantum Hall state and can produce a quantized Hall effect. Yeah, we'll take this is a real Coulomb interaction. This is a Hamiltonian that we'll apply to our wave function. It's nothing to do with the plasma mapping. Well, the plasma is the plasma. That's just a wave function. That's okay. Okay, and so the key point here is that screening in the plasma mapping that we had for the wave function leads to the actual fractional quantum Hall effect. Okay, so we have quasi-particles, and I've mentioned that we have Q types, and so I've implicitly mentioned the fusion rules already. So we have Q types, and we have charges little q over big Q, and so if we imagine that we have these formal symbols, phi sub q, q is running from 0 to q minus 1, then the fusion rules are simply that the fractional charges add. Phi q1 times phi q2 is phi q1 plus q2 modulo big Q. So these are the fusion rules, and there's only one term on the right-hand side, so these are abelian fusion rules. And as I think Chetan mentioned, So this is just the multiplication table of an abelian group. It's just a cyclic group. Okay. Okay, so the kind of hand-wavy argument about there being an energy gap can also be applied if I want to use the special Hamiltonian for which the ground state is exact, as opposed to this variational point of view with trial functions. The quasi-Hall state in that case is an exact eigenstate, but the quasi-electron is not an exact eigenstate. So we still use a variational point of view, and we still expect a non-zero energy gap. But that doesn't mean that we can prove that there's an energy gap for that special Hamiltonian. Okay, so these are the fusion rules. So what the next thing, obviously, is to think about statistics of quasi-particles. Well, if I'm honest, I'm doing the calculation for quasi-holes only. And so this was done by Rovers, Schriefer, and Wilczek. It's possibly the most prominent et al. In history. Okay, so what we want to do is we want to have a couple of quasi-particles labeled by little q1 and little q2. And calculate what happens if we exchange them. Well, if I want to exchange them, maybe I should make them the same, since I said it wasn't all that meaningful otherwise. But I could consider the more general thing if I keep in mind it's not completely unambiguous up to gauge transformations. So we'll have W1 and W2. So we want to calculate the Berry phase for such an exchange, or braid, or even for more general braids. So let's go back to the Berry phase, which Charlie talked about yesterday or the day before, from about 1983. So in very general terms, we have, I won't even use a Hamiltonian here, I'll just say that I have some parametrized family of states. So let's say I have a state psi of S. S is a parameter. In fact, S is just going to run from 0 to 1, and this is going to parameterize a closed loop, in fact. So let's assume that psi of 1 is equal to psi of 0. So then what Berry taught us was that we can first define the connection, or if you like, the derivative of some phase. That's the way I'm going to write it here. So we take d psi by ds, take the overlap with psi of s, multiply by I, and that's this derivative. This is the Berry connection. I seem to have a different sign from Charlie for some reason. And then the phase that's picked up on adiabatically evolving around this closed loop from 0 to 1, the adiabatic phase is the exponential of I times the integral ds of d gamma ds. Okay. And I've removed any dynamical phase. If you want to think of adiabatic transport, you should think of a Hamiltonian and time, and this is done very slowly as the parameter changes slowly. In that case, there's a so-called dynamical phase, which just comes from the energy of this what is usually assumed to be an eigenstate at each time, and you accumulate that phase as well, but that's less interesting, so it's removed. Okay. I mean, for this setup, you could sort of calculate, you can imagine, since we're talking about trial functions, you can take these functions parameterized this way, some states in Hilbert space. You could do this whole calculation. You never need to, if you just want to calculate this, you're free to do so. You never need to say that this is an energy eigenstate or refer to any Hamiltonian. You can just calculate this. In practice, we would like to imagine that we have eigenstates, or at least we're doing calculations with trial wave functions for eigenstates, as we were writing here. Okay. Yeah.
So if we're going to come back to the same wave function, we have to do the full break.
Yes. Yes. Yeah, so only that calculation will really be meaningful. In fact, I know. I mean, it's just simpler to draw that picture, really. Okay, so let's just try to calculate this for one quasi-hole. So we have this function d psi Laughlin plus w. We'll take the derivative. Let's just take the derivative of the function. So w depends on s in some fashion. W is going to go around a closed loop. So we can just take the derivative of that function I wrote. So we get minus dw ds. Then we get, if you realize that it's a product, that means that we get sum on I 1 over zi minus w times the same function. Okay, and this is still a lowest lambda level function because although I've got 1 over zi minus w, I've got factors of zi minus w here, which are just being removed by this. I mean, after all, that's what happens when you differentiate. So that's what we get. And then we can write this as minus dw by ds. And I can introduce a dummy variable, z prime. Then I can write the particle number density n of z prime divided by z prime minus w psi Laughlin plus w, where n of z prime is sum over j delta zj minus z prime. So that's the particle number density operator in first quantization. Okay, so this now we're going to calculate this Berry connection. Now you remember that psi was supposed to be normalized, and the Laughlin wave function was never actually normalized. So we have to remember to consider the normalization now. And that turns out not to be too difficult, because I can normalize the Laughlin wave function by dividing by the square root of the norm square. Norm square means I have to integrate the mod square wave function. And I'm going to calculate gamma, or d gamma ds, I'm going to have to take that inner product anyway. And so differentiating the normalization factor just produces the same derivative of the Laughlin wave function and also of the conjugate wave function that I have here. So when the dust settles, the effect of the normalization is not just to multiply this by the conjugate of psi and integrate over the particle coordinates, but to divide this contribution by 2 and subtract the complex conjugate contribution. So that's z prime. Yeah. So I get integral d2 z prime 1/2 1 over z prime minus w dw by ds minus 1 over z bar prime minus w bar dw bar by ds times the expectation of n of z prime in the state, which is still the Laughlin state plus the quasi-hole. Okay, so it boils down to this, and this doesn't look quite so bad because it basically involves an integral with the expectation of the density and some other factors. Okay, so again, the step from going to here to this involves taking care to normalize the function, the state, which I think is actually left out in the paper, but somehow they got the right answer. Okay, so that's checking this is a very good exercise. Checking this step. All right. So now we have to analyze this, and we have to take care here. See, eventually I could try to integrate over S as well to get the net Berry phase, and I might try to do that by doing that integral first and going under here and using Koshish Theorem or something. However, there's a difficulty, which is that this expectation of density depends on W. So it's not obvious that I can just do the next attractive-looking step. So I have to worry about the fact that this depends on W. Okay, so what we know about this expectation is, which we've already discussed, is that in the ground state it would just be uniform out to the radius of the droplet. When we have the quasi-hole, we have a hole in the density at W, and we also have some corresponding compensating charge pushed out to the boundary, to the edge. Okay, and other than that, these changes in the density compared with the ground state fall off exponentially with distance from either from W or from the edge. And okay, so to really make a convincing argument out of this, what I want to do is suppose that I subtract off the expectation of n of z in the ground state, so I'm not writing plus W, and then I have delta n1 of z plus delta n2 of z. Okay, and what these are, delta n1 is the difference in the vicinity of W. So this is only non-zero for z near W. It goes to zero exponentially fast away from W, which is an implicit argument here. And delta n2 is non-zero only near the edge, likewise. Okay, so I've separated those two pieces. And so if I take these two, delta n1 plus delta n2, and integrate over z prime, I get 0. See? Okay, I might have some water. Okay, so now I want to argue that the delta n1 and delta n2 don't contribute to the Berry phase. Okay, so let's look at this. So delta n1, z prime minus W. Well, another thing I could have mentioned about the delta n1 part, this is the density deficit at the location of the quasi-hole. Well, thanks to screening and the rotational invariance of my system, delta n1 is rotationally invariant about W. Okay? Whereas the factor in the denominator, of course, has a varying phase. So this integral gives me 0. Okay. Now, of course, this is really because of screening. The fact that I can separate these is because I have screening in the system, and W is far from the edge, which I should have made more explicit. Okay. So up to exponentially small corrections, this is true. So then we can think about delta n2. So again, this depends on W and is only non-zero on the edge. So here what I'll do is I'll try to estimate this. We'll take the absolute value. Then we can bound this by the same integral of the absolute value delta n2, and in the denominator, if W, well, that's supposed to look circular. If W is near the center somewhere, and this contribution is non-zero on the edge, then Z minus W is of order the radius of the droplet. One can be a bit more precise, but it's basically the radius of the droplet. Okay. And so this is, in other words, this is of order 1 over R. So delta n2, well, so it pushes particles outwards. It may oscillate a little bit at the edge, but there should not be anything dramatic from the numerator, so it's basically of order 1, and so this integral is going to 0. It's not going to 0 exponentially. Well, okay, so one could say a bit more here. For example, if I put W exactly at the center of the drop, I could again argue that this is 0 by symmetry, which means that if I move W away from the center, in fact, I've overestimated here. This bound is correct, but I should be able to say it's really going as 1 over R squared, and not just 1 over R. So it's going to 0, but I don't know if I can prove that it goes to 0 exponentially in this case. Okay, so anyway, if we take the large radius limit, this goes to 0. So that means that I can finally replace the expectation in the state with the quasi-hole with the expectation in the ground state. And now I can integrate. So now I can write gamma of 1 minus gamma of 0. It's minus I integral d to z prime. And I have a half. And I have dw over z prime minus w minus dw bar, z prime bar minus w bar times n of z prime. And this last factor does not depend on w. In fact, it's just a constant inside the edge of the droplet, essentially. So now I can do the w integrals first. If I take these two separately under the z prime integral, then I can use Koshish theorem. And let me assume that I'm dragging w of s is just a simple closed curve that doesn't intersect itself. Then what I get is minus 2 pi. And I can do the other term in the same way. I get minus 2 pi, the integral over the interior of the loop of n of z prime expectation. And of course, this n of z prime is just n bar in the interior of the system. So this is a periphase, which is, since n bar is constant, this is just minus 2 pi, and I have nu over 2 pi times the area enclosed. So what I've got is minus 1 over q times the area. So this means, this is like what happens when you move a charged particle in a magnetic field. You pick up a phase, or when you move it adiabatically in a magnetic field, you pick up a phase which is the flux through the loop. So this is the same result that you would get, quantitatively speaking, it's the same as you would have for a charge minus 1 over q in the same magnetic field B. I think B is 1 in my units, in fact, which agrees with this. Any questions? Yeah.
So just to make sure I understand this last expression, W is the coordinate of the quasi-particle that can be.
Yes. No, there's only one quasi-particle. I haven't got to statistics yet. I only have one quasi-particle. So all I get here is this Aronoff-Bohm phase. It doesn't matter where I do this loop, I just get this area term. And in a second, I'm going to have a second quasi-particle quasi-hole and calculate statistics. Yeah.
But technical question on that point. In the first step, we're taking 1 over ZI minus W times the log length plus W. Why don't you just get log length W? Like slide log?
Well, this is a sum, and the other one, if it's still there, is a product. So it's a product of Zi minus W in the state, right? This contains a product. Differentiating the product is why I get a sum. Get one term for each factor in the product. Okay, so now I can do the case of statistics in this very small corner of the board that I have left here. So we basically do the same thing now. And here's my W1, and I can consider a second quasi-particle at W2. By the way, if I did this calculation and I had little q1, instead of just not equal to 1, but bigger than 1, then that would just come in as a factor in the answer here, okay, corresponding to the fractional charge of those quasi-holes. So I could take one of charge q1 around a second one with charge q2, or q2 over big Q. And so I can go through the same arguments if you want to very carefully check things, but the main point is that if I get rid of the contributions from W1 by these arguments I used here, I would still have the charge deficiency of the additional quasi-hole at W2 sitting in this guy here, in this density. So this would not be uniform, and there would be a net deficiency of density. So that when, so let's say here, for example. So then here I integrate the density, but now there's some density missing, and the net amount of particle number missing is 1 over Q. So then here, in this case, I get an extra, for Q1 equals Q2, let's say. I get an extra Berry phase. The change in the Berry phase compared with not having the second quasi-particle is 2 pi over Q. Okay, due to the missing part, which is the integral of change in the integral of n of z prime, is minus 1 over Q. Yeah.
What's the length scale that sets whether these two quasi-particles are well separated?
It's sort of order the magnetic length, which is of order 1. You might want to throw in a square root Q. But this plasma is rather strongly coupled, so the screening length is not much different from the particle spacing. It's not like the weak coupling Debye-Huckel limit. Question? Just stretching? Yes. Okay, I guess I'm equivocating between doing the more general case or not. Let's just do the case where they're both equal to 1 for the first case. So a similar but slightly more tricky calculation is to argue what happens if our parameterizes moving both of them simultaneously. Okay, and in fact what we want to do is we want to exchange them like this. Okay. In fact, you can argue that it's really the same as taking what I have here, where I took one around the other, and just doing half of that. If I take one around and I go halfway, well, then I can shift them over and bring them back to their original positions, and then that's an exchange. That's a little bit sloppy. It's a little bit like taking a square root, which would be subject to some ambiguity, plus minus 1. But you can argue around this in various ways. You can just try to do this more complicated geometry here. Directly, you can just argue this. And so then what you get is delta gamma is pi over Q, half of what you had for this. So this is like the double exchange. In other words, this is going around twice. Okay, so this is delta gamma is pi by Q. So if we think of statistics, the phase as e to the I theta, it means that theta is pi over Q, big Q, for the Laughlin quasi-particles. So that's the result from a Rover, Striefer, and Wilczek. Okay. And then we can generalize, and I guess I'm forced to use another board. So we can generalize if we have, so if we do the double exchange for, if we do the double exchange for one with Q1 and one with Q2, then we get delta gamma is 2 pi Q1 over big Q in the general case. So as promised, these things multiply, as we discussed the other day. Okay. And we can do some little cross-checks on these formulas. Let's go back to this case with little q equals 1. Well, let's see. Okay. So if they're identical, let's just do one more thing here. So if they're identical, Q1 equals Q2, then we can just do the exchange, or the statistics, instead of the double braid. So then we have this phase is pi Q1 squared over big Q. So if we take Q1 equals big Q, then we find that we get bosons. This is a boson. This is a multiple of, if Q is even, we get Q squared over Q, which is Q. So we have an even multiple of pi. We have a multiple of 2 pi. So we have, in other words, we have delta gamma is 0 mod 2 pi. So they behave as bosons. But if Q is even, Q is odd, then we have delta gamma is pi mod 2 pi. So these are fermions. So I've already argued that capital Q quasi-holes is equivalent to one real hole, and that real hole should have the same statistics as the underlying particles, which are bosons when Q is even and fermions when Q is odd. So that's what we have. So we've recovered that. You can even calculate statistics of ordinary particles of electrons from adiabatic transport. Yeah. Well, those are related because the density in the interior is a constant. So those are not two separate limits. That's the same thing. And so that's the limit that's used. The assumption was that we have screening. Because of screening, when things are far apart, in most cases, that means corrections are exponentially small. And I discussed the status of the correction terms explicitly over here. Okay, other questions? Yeah. Some people claim that they've in some way measured the exchange statistics in some slightly indirect way, with probably involving transport and shot noise, not shot noise, but interferometry, basically. Yeah. I think not everyone is really convinced that it's a convincing measurement. Although it may be that the objections are slightly philosophical or uncertain, not about the experiment, but about the interpretation, whether some effect that's measured can really be viewed as a measurement of the fractional statistics, because it has to be rather indirect. You're certainly not going to literally exchange two things and measure the very phase. Although interferometry is something that in principle can get close. One of the problems you see is that you would have to separate off things like the Aronoff-Bohm phase. You have to be able to avoid that part. So you want delta gamma, not gamma. Okay. All right. So this is all I'm going to say about the Laughlin state and quasi-holes for the time being. Maybe I can sum up this bit. So here, what we have here then is an example constructed from trial wave functions, many of which are even exact eigenstates of some particular Hamiltonian. And we've obtained an abelian topological phase, and we can calculate the fusion rules and statistics in this topological phase. In fact, we can also calculate lots more things that I'm not going to talk about here.
All of this is assuming that its hole is placed in its extrinsic defect. Is there any way to give it?
Not really. No, I'm not assuming it's an extrinsic defect. In fact, it's an excitation of the system. You know, the system contains states. This is an excitation of the system.
We're choosing W fixed.
Well, I have said that it's fixed, yes. So you can think of this as a coherent state. So the quasi-hole, if you consider an actual Hamiltonian, and you imagine this is a good approximation to states. So one thing is that because the quasi-hole, if you like, because it behaves like a charged object in a magnetic field, the states for the quasi-hole, the single quasi-hole, you should think of them as being like Landau level states. So there's going to be a degenerate set of states. So if I make this state at some point, it's just going to sit there. Okay? And so that's the kind of dynamics that it has, and that's all, actually. So it's not that it propagates off like a particle with some mass or something. That's the main thing. So you could also say that it's like a coherent state packet, although we didn't talk about those here. So, yeah. I mean, sometimes, if some people describing this adiabatic calculation would really like to say that they have a Hamiltonian and they vary a parameter in the Hamiltonian slowly, and then you could use some sort of potential term that traps the quasi-particle and use that to drag the quasi-particle as you wish. So. But I would emphasize that it's not an extrinsic defect, it's an intrinsic defect. It's a quasi-particle excitation. Okay, all right. So this is a sort of stopping point. I'm going to switch to something a bit different now. So this is my first real example of a topological phase after 3 lectures. Okay, and it's abelian. All right, so let me go back. Maybe we'll go back over here. So what I want to do now is continue with fractional quantum Hall, but I really want to get to non-abelian quantum Hall states. Yep. Yeah. Mm-hmm. Well, ultimately, so what we want to say is that we're representing a phase with a trial function. It's a kind of paradigm, gives paradigm behavior for this particular phase. And of course, in a topological phase, the things that we can calculate, the things we're most interested in are the things that are supposed to be robust within the phase. And that's basically the argument that Laughlin made, although, that was at a date when we hadn't really formulated those things. But the argument was, well, this is a trial function. This captures the physics, meaning that whatever the exact ground state really is, it's certainly not the Laughlin state in general. The ground state and quasi-Hall excitations have the same properties that you can calculate from the Laughlin function.
For that philosophy, the assumption is there exists a local that far away.
If you want to use that literally as an eigenstate of something, yes. If you want to say that there's a
So there's an assumption.
You could try to argue that way, yes. I mean, you could try to say that there is a Hamiltonian for which it's exact, and the quasi-holes are exact. We can't prove that it has a gap, but it's extremely likely and plausible that it has a gap.
So it's a reasonable assumption, but it is logically that it's relying.
Yeah, sure, you can say that. Yeah. You could also take the view that, well, what we've done is, apart from constructing wave functions and things, we can identify it with some consistent solution to all these consistency conditions for a topological phase that we have quasi-particle excitations, we know the fusion rules, we have fusion rules, we have statistics, which is all consistent.
But that doesn't guarantee that. I mean, it's like the story with writing down these, I don't know, other CFDs where you can write down wave functions.
Yeah.
But maybe they correspond to catalyst states. So,
Yeah.
So there's more that.
Luckily, no one knew that when Laughlin was doing his thing. Yeah, sure. So you can try to, but actually you have a kind of preponderance of evidence. You can argue that this whole picture makes sense from different points of view. That's what I was trying to say. So one is you could actually use Haldane's special Hamiltonian, for which these are actually eigenstates. Unfortunately, we can't prove rigorously that there's a gap. Okay, but then you can make it very plausible that way. What else can you do? Well, you can also argue that if we take our general understanding of modular tensor categories of topological phases, this is a consistent example, and it's consistent with including things like unitarity. And of course, other things you can do are you can construct an effective field theory that also tells you that there's a consistent effective theory. So you have a great many bits of evidence from different directions. But I think the question was motivated slightly differently, which was that whether I'm using the same philosophy that I was using before. So there what I was trying to do was to motivate the concept of topological phases and argue that topological phases exist. Here I'm attempting to construct an example, and I'm understandably using slightly different arguments. Yeah, well, there's plenty of evidence. I mean, you can think of this as a variational. You can use the pseudopotential or the special Hamiltonian, or you can use variational arguments that once you have the Laughlin ground state, and you imagine that this seems to be a nice ground state that picks a particular filling factor. It's not an arbitrary filling factor, but it's a particular one that happens to be what they had observed. Then the existence of fractionally charged excitations follows kind of automatically. It's low energy object. If you took a random state in Hilbert space, you're not going to get low energy. Okay? Getting low energy means that the system locally, because interactions, even with Coulomb, it's basically short-range interactions. So to get a low energy, you have to be locally similar to the ground state. In fact, you have to keep the particles somewhat far apart. I didn't emphasize this point. I probably should have. The point about Laughlin's function is the wave function vanishes rapidly when particles come close together. So the particles tend to stay apart. If you look at the density, and consequently density correlations fall off exponentially. You can even look at a snapshot of a typical configuration in the wave function. And instead of being like Poisson distributed, the particles are sort of avoiding each other in a consistent way. They're random, they're not forming a crystal, but they're well spaced. And that gives you a low interaction energy for a repulsive interaction. And so to keep that when you have a quasi-particle excitation, to avoid having infinite energy in a large system, you need the system locally to resemble the ground state, except perhaps at this intrinsic defect. Yeah.
Is it possible to put pseudopotential Hamiltonian contours?
Yes. It's Q. Mm-hmm. Yeah, so there's other you can write the Laughlin function in other geometries, the sphere, the torus, which I haven't talked about. Okay. It's a little late for this. Okay, well, it's a little late, but anyway, let's get. So I want to say something about conformal field theory constructions for trial wave functions in the fractional quantum Hall effect. So this means warning, dangerous bends ahead. So this is from our work in 91. And this is really a bad time to start this. Well, we can do a little bit, but all right. In order to actually use some time, I'll do a little bit, but we're not going to get back to quantum Hall wave functions for a little bit. So let me just switch gears. So we're not going to go very far into conformal field theory, but we're just going to use a bit of field theory, really. And the fields happen to be massless. So suppose that we have a massless, as my basic example. Let's take a massless scalar field in 2 dimensions, which are Euclidean dimensions, not 2 plus and not 2 plus 1. So the action is just the grad phi squared. And there may be some factor I should include. I'm not sure what it's supposed to be, so I'm just going to leave it out. And so solutions to the equations of motion, which is just the Laplace equation. If I think of them explicitly, they really, in general, can depend on z and z bar. Again, z is a complex coordinate, x plus iy. So solutions have the form of a function of z plus a function of z bar. Because del squared is basically 4 d2 d by dz bar. So any function of z or any z only or any function of z bar only is annihilated by this. So so these fields, these solutions, can be split into right and left movers, or holomorphic and anti-holomorphic parts. So something that's a function of z only, something that's a function of z bar only. Okay, so these are holomorphic and anti-holomorphic. And the correlation function for the field phi, for phi of z, so-called chiral field, I'm just going to say is minus log z. I'm sweeping some things under the rug here, but let's just say it's minus log z. And in particular, this is the definition I want to use, which determines, well, it determines the normalization of my phi. The coefficient in front of the log has to do with the normalization of phi. This is a little problematic because phi is not a very good field. It's not a good conformal field. We won't worry about that too much. The main point for our purposes is that here we have this field. Well, it's like a scalar potential, if you like. And this log is like that two-dimensional Coulomb interaction that we had in the Coulomb plasma earlier, in the two-dimensional plasma. So we're going to exploit that, basically. Okay, so let's look at a correlation function. And I'm going to have to explain how to calculate some correlation functions a bit. So let's take a correlation function which contains n fields and some other operator O. And A of z is a field which is e to the I phi of z over square root nu. And this is something which is viewed as a charged field, so this is going to correspond to a charge in the plasma eventually. And O is a similar thing, which, so if this represents a charge at z, this is going to correspond to a whole bunch of charges, meaning a uniform charged background. Okay. So this is not a sort of local operator, because in the exponential I have an integral of phi. Okay. So if you like, this is like taking these things with some point charges, small point charges at many places, and then taking a limit so that it becomes a continuous density. And that's a point of view that we will need to use. Okay. So now let's, because I imagine that there are people who haven't done calculations with this kind of thing in field theory before, so let me just do this. Although this is very much like Lussenger liquid stuff, it's another language that's, Lussenger liquid and the conformal field theory of a scalar field are pretty much the same thing. Okay? All right, so let's just look at how you calculate some exponential of this type. Suppose I have e to the I phi over root nu and at z, and e to the minus I phi over square root nu at 0. So, naively speaking, what you do is you expand the exponentials. Okay, so we have an exponential series. And the next term, if I have to look at my notes for the exponential series, so then we get phi squared of z and so on. And then inside here we have 1 minus I phi over square root nu at 0 minus 1 over 2 nu phi squared of 0 and so on. We'll use Wicks Theorem. Yes. So Wicks Theorem, everyone ought to know Wicks Theorem, but Wicks Theorem says that when you have a correlation function of these non-interacting fields, you just have to contract in pairs. You pick out phi's in pairs, and for each pair, you write down this two-point function, and you have to sum over all ways of choosing the pairs. Now, the other thing here is that we get unpleasant singularities when I have phi squared of z, for example, if I contract this with itself, then I get infinity. That's bad. But we can get rid of those, at least in some formal sense. We can get rid of those by imagining that, so what I will assume is that we've actually normal ordered these exponentials. And normal ordering basically means you never contract these things with themselves when they come from the expansion under the inside of normal ordering. So each of these exponentials is normal ordered. So then we don't contract this phi of z with phi of z, we only contract phi of z with phi of 0. And then we can go through this, and so we get minus 1 over 1 minus 1 over nu log z plus 2 over 4 nu squared log c squared, and so on. And in this particular case, it's easy to do the combinatorics of the contractions because there are n factorial ways for the nth order term. So first of all, we have to pair up all of the phi's. So I have to take contractions of the nth order term in phi of z with the nth order term of phi of 0 to get a non-zero result because of normal ordering. And when I have phi of z to the n, there are n factorial ways to choose the pairing with phi of 0 to the n, so that I cancel one factor of n factorial, and this is actually an exponential series, and I end up with 1 over z to the 1 over nu. Okay. So if you've never seen this, this is definitely a very instructive calculation with a massless free field. There are other variations on the same thing, where this exponential, this correlation two-point function of exponentials of a scalar field give me a power law. So again, this means basically that e to the I phi of z over square root nu, this has power law correlations with the opposite field, and this is a conformal field theory. At least we have scale invariance, and so this is a field that has nice scaling behavior as a power law correlation function. Okay. About no, I didn't put that in my example two-point function. But on the other hand, what I did put, and this is what I wanted to say now, is that I put e to the plus I here and e to the minus I here. Because one of the rules that comes from this game which you can trace back to the fact that shifting phi by a constant is a symmetry of this action. So if I shift phi by a constant, that's a symmetry, and so the consequence is that the sum of the charges, the coefficients in the exponentials, has to be 0. If it's not 0, if I had plus here, when I shift phi by a constant, the whole thing will change by a phase factor, which is arbitrary, and that means the correlation function vanishes. So to get a non-zero correlation function, let me write the kind of the general correlation function. I might have product of I, e to the I, or j, q sub j, phi of zj. Suppose I want to evaluate something like this. The rule is that this is 0 unless the sum of the qj's is 0. So I have to have charge neutrality because of the symmetry. Okay, so this has to be charge neutral to be non-zero, and now I'm almost back to what I wanted to calculate here. Here I wanted to calculate with a bunch, because these are identical things, I have n charges of plus here, n coefficients plus. So the role of the O is, although this is spread over some uniformly, this is basically charge with the opposite sign. So the role of this is to make the whole thing neutral to give a non-zero answer. And so then the punchline, which will be the last thing I say, is that this correlation product of A of Zj is, so in general, for each, so something I should have explained is that when I do more than two fields, I get a factor like this for each pair, because it's all multiplicative. So what I get is Zi minus Zj to the 1 over nu for I less than j, and something which I will claim anyway is basically the Gaussian factor, the interaction with the background. Basically, these are reproducing, these exponentials of phi are reproducing correlations in a plasma which may contain both positive and negative charges, or Boltzmann weights in a plasma, rather. This is a little bit sloppy because the charge density here, so really to make sure it's neutral, I should restrict this integral here to a disk of radius r, so I have a finite net charge. The net charge here would be the integral of this rather than the sum. So the net charge should be 0, so I need to restrict that, and the consequence of restricting it is that this form would not be exact. It wouldn't be exactly this. But in the interior of the drop, it definitely looks like this. So this construction, as I've written it here, would differ. This is basically the Laughlin wave function. Strictly speaking, it differs a little bit outside the droplet. But inside the droplet, where I want to use it, it's exactly the same as the Laughlin wave function. So this is the reconstruction of the Laughlin wave function from this massless scalar field theory. And that will be a good place to stop. Did you have a question? Someone's just waiting for me to end. Yes, Sergey. Yeah. I probably violate the symmetry or something. I don't know if I can explain that.
If you just do it by Gaussian integral,
yeah,
you'll get an additional factor that diverges, that has sum of q's in the component. You get a minus sum of q's times something diverges.
Mm-hmm. Yeah. Right. Yes. Yeah. You can just try to attack the correlation directly as a Gaussian integral. Yes. Thanks. Yes. Good. Well, when it is neutral, this gives you the answer. Let's just say that. Yeah. Well, I think where we were coming from was that I worked on fractional quantum Hall, and Greg had worked on, obviously worked on rational conformal field theory. And the underlying observation was that the structures that arise in rational conformal field theory are the same ones that are consistent particle statistics. So we said, why don't we try to find a fractional quantum Hall state with non-abelian excitations? And that was the starting point. But from there, we started to say, well, why don't we just use conformal field theory correlate? I mean, the Laughlin state looks like a conformal field theory correlator. So why don't we build on that to make trial wave functions? Yeah.
A little bit of follow-up of the previous question. A little bit. What about what if that and at the end of the day?
Well, what's peculiar about it? If you forget about this part, which many people do, forget about this. Maybe you can just put some big lump charge off at infinity or something instead. If you forget about that, if you know something about these kind of correlation functions, then you know that this is the kind of thing you get. Sometimes you have the exponents might be plus and some other exponents might be negative when you have different size charges. But that's kind of known. Some people were puzzled because these are all plus. But the answer to that was already contained really in Laughlin's work, you see. It's a plasma with a neutralizing background. So it's not some kind of funny non-unitary CFT. It's an ordinary CFT. But the CFT is underlying it. In a sense, what we're doing is perturbing CFT. We're not constructing a CFT. Yeah.
So there's always this argument about charge conservation, having these Q's add up to 0.
Uh-huh.
And the argument is that you can shift phi by constant, the argument that you gave.
Yes.
On the other hand, if you were in 3 dimensions, somehow you couldn't give that argument because you could have spontaneous symmetry break.
Yes.
So somehow 2 dimensions. The fact that
Well, 2 dimensions is certainly different. In 3 dimensions, what happens in 3 dimensions if you took something like this is you still have the symmetry, obviously, but the symmetry breaks spontaneously, and here it doesn't break. That takes us back to Kosterlitz-Thalers. I wanted to mention actually that, not additional stuff, but the same thing. I wanted to mention that these kind of calculations, I think the string theorists were already using this by the early 70s. Then there's Sidney Coleman's bosonization paper from about 75, and then once again Kosterlitz and Thalers. Some of this appears there, I think. Also about the same time, and other people in condensed matter using similar techniques. And this is Luther and Emery and other people. This is really early Lussinger liquid stuff in parallel with Coleman. And secretly, actually, Kosterlitz had worked in string theory a bit before he did his work. Not many people know that. So that's where this kind of stuff comes from as background references, early ones. Yeah.
You said at large Q, this wave function transitions to some kind of crystalline phase.
Oh, you keep coming back to this.
Yeah, do you see that in the CFT?
No, the CFT just gives us the function. And it doesn't care what Q is. It just gives us the function. It doesn't tell us about the stat mech of the function because we're not doing any integrals over z. So, to look at it as stat mech, you have to take the mod square and integrate over the zi's.
Okay.
This is just a function at this point. And then there's the question of analyzing the function.
What's the radius of this boson matter?
Well, you can. The way I've done it, I haven't compactified it, so there isn't a radius. Okay, but that's why I said, well, there may be some. I need a coefficient here, but what I really want is the coefficient here. In terms of relating it ultimately to some compactification, that's all contained in my choice of q, or nu. That's related to that. So the radius squared is q or something. Yeah. Yeah, well, the CFT is a two-dimensional theory, and the fractional quantum Hall is a three-dimensional theory. So you can't make this kind of direct comparison. Well, okay, let me reformulate the question. The question really is, why are you using correlation functions in 2 dimensions to describe wave functions in 2 plus 1 dimensional systems? Well, that's what we wanted to do.
I mean,
That's
this
our
one
choice.
that's the way to generate.
We've
waves,
done it.
right?
We're doing it. There is a kind of many years after we did this, we realized with Jérôme Dubai, we realized that there is a way that you can kind of put this into a broader context, which is kind of relating it to matrix product states. But this, I think, takes me a little bit too far afield. You can think of this as a kind of glorified matrix product state where the bond dimension is infinite. It's the Hilbert space of the CFT.
Does that allow you to make contact with the fact that the same CFT describes the edge?
Yeah, I guess so. Yes. I mean, we can make those kind of arguments anyway, of course. So it's not, you don't necessarily learn anything new from making this relationship, but it maybe makes you feel a bit more satisfied. It makes you.
Plus one.
Yeah. No, but that's not the point. The point is why are you describing a bulk system using a 2D CFT? So this 2D CFT is like the auxiliary variables in the matrix product state. And then we have these operators which are like the tensors. These operators here are the tensors. In CFT you can use radial quantization. If you go out radially in space, that's in the auxiliary space. And these operators are the tensors. You do the contractions in the auxiliary space, that's taking the correlator in the 2D theory, and this gives you the wave function. So that's the matrix product state. So there's kind of a conceptual connection with other things. And interestingly, this has also been the basis for very powerful numerical work by Zalatel and Mong at about the same time that we were saying this, in fact. Which is perhaps a bit more important than just saying, well, you can interpret something as something else.